Come on in, everyone. Sorry, just got here under the wire. Anybody have any questions before we get started? No questions? We only got like 5 of you in here right now, though. Oh, we're up to 7 now. All right, so no questions before we get started. Hopefully y'all did well. I haven't looked at the grades or anything yet. I do know that there was a problem. Remember, I think I told you guys, or actually y'all probably told me about it. I think it was y'all, where basically I included chapter 26, which I wasn't supposed to do. So you'll definitely be getting those points back, probably as extra credit if you got them right. So your grades are definitely going up. No matter how bad you did, you definitely did better than you originally thought. So hopefully that'll give you a good weekend. I may send you some messages over the weekend just to let you know some things, but as far as everything goes right now, y'all just go have a good time and all that good stuff. What I want to do now is we're going into the next chapter after magnetism. We're going into sources of magnetism, and I do it a little differently than your textbook does. Your textbook starts off with the Ampere's law. Or actually, it starts off with just giving you an equation for the magnetic field due to a current carrying wire. Then it works out Ampere's law, and then it gives you a bunch of examples with Ampere's law. Then it introduces the law of Biot-Savart, which is much more complicated to apply than Ampere's law is, but it's universally useful. Whereas Ampere's law, if you're using it like we're going to use it, which is to solve for the integrand, namely the magnetic field, then it's pretty straightforward to do. It's like Coulomb's law versus Gauss's law. Gauss's law was a lot easier version, but again, work under certain symmetries. So anyways, let's go ahead and get started. I'm going to start off with a derivation, or at least an argument for exactly what the law of Biot-Savart is. So I'm going to start by sharing my computer screen. And we're going to introduce the law of Biot-Savart. Remember, these notes are on my Google Docs. You can know the name by just looking up the date. So for instance, today's is called PHY242N01B underscore 11022023. So that's what it would be named in my Google Docs page. So you can check that out. Let's start off with, oops, I don't want to write in black. The Biot-Savart law. Okay. So what the Biot-Savart law does is it gives us a way of breaking down a continuous body carrying current and doing so in such a way that you can take one of those itty bitty broken down parts and calculate the magnetic field due to that little part. So let me start with giving you a sort of a three-dimensional coordinate system, just so we can have some understanding of exactly what the symbols we are using are. So this coordinate system is in fact going to be the x-axis, the y-axis, and then the z-axis will point out. Remember, it has to be right-handed, which means if you take I hat cross J hat, it better give you K hat, not K hat. So once you've drawn the X and Y axes on any three-dimensional coordinate system, you have no choice of the Z axis. It has to be mutually perpendicular to the X and Y, and it has to be in a direction that's consistent with the right-hand rule, such that I hat cross J hat equals K hat. So let me show you what we mean here. So imagine we have a wire carrying a current like this, okay? And let's also imagine that we have a location in space, let's say right over here, and that point is called P. And that's the point at which we wish to know the magnetic field. Okay. What we can do is we can define a vector that points from the origin to that point P. And that vector is going to be called R sub P. So what I will do is I am going to draw that with a green vector like that. And that vector, as I said, was called R subscript P. Now we can also, for instance, calculate a differential tangent vector. In other words, a tangent vector to the wire that's carrying current. And we're going to assume right now that the current being carried is I, and it's going along this way. Okay. So that's the battle plan anyways. And ideally, I would like it to, for you to easily see my vectors. And that might be a little bit of a problem unless maybe I stick it. No, that looks really bad. That looks worse. Let me try, actually, okay, I'll just do it like this. I'm going to say that the differential vector, the little differential tangent vector, whoa, Nelly, let's just erase that whole thing there. Actually might be the best answer. So let me do that real quick. I'm going to erase a big chunk of it and go from there. So let's say, I think if I change this little piece of circuit, I can make it look a little better. And that's what I'm going to attempt to do. So I'm going to take this and assume this wire goes, instead of like the way it went before, it's going to go down and like that. Yeah, that works pretty good. So now what I'm going to do is I'm going to say there is a tangent vector right here, and the vector that points to it will be called R sub dl, where R sub dl is the vector that points from the origin to the differential line element dl. So let's take our little green vector. I'm going to draw it a little thicker than I did this time, last time, excuse me. And that'll be the actual vector right here. This vector is called R sub dl, and it points to the vector dl. And as I said, dl is going to be a tangent vector. So it, at the point, the little black dot there, it'll be parallel and points in the direction of the current. So there's our little dl vector. Okay. So it turns out that if this is a scenario you have and you wish to know the magnetic field due to this little differential line element that happens to be parallel to I, notice it's going the same direction as I. So that means I also need to correct that. So let me fix that real quick. So as long as the dl vector is going the same direction as I, then you can use this Biot-Savart law to calculate the portion of the magnetic field at P due to this little section dl as, here it is, dB is equal to mu 0 I over 4 pi. And then you have to take the vector dl and you have to take a cross product of that with the vector. Now, what we're really doing here is we're attempting to find this vector. Yeah, I'll just use a red vector. What we're really trying to do is find a red vector that points to, oh, that didn't go out so well, did it? That points to the position P from the position of DL. So let me just draw that over because it turned out like crap. All right, so I'm going to draw a vector here. And that vector is supposed to see if I can force it on this line like I want it to be. Okay, it's supposed to be the vector that points from DL to P. That's the vector I want to take the cross product of DL with. So I'm doing DL cross. Now I take that vector that points from the little differential line element to the P. I think you can see that that vector is actually related to RP and RDL in a very specific way. Can anybody see exactly what way RP and RDL are related to that little red vector I just drew? Anyone? Let me put up the comments in case somebody's typing it in. Move this out of the way. Nobody has any guesses on that one? So what can you do with RP and R sub DL to make a vector that points from the end of RDL to the end of R sub P?
Are they added together?
If they added, you would get one. Remember, you have to move the tail of RP to the end of DL, or the tail of DL to the end of RP, and then connect from the origin all the way there. That sort of almost goes perpendicular to this little red vector that I'm showing. And I mean the long red vector, not the DL. Anybody have another guess? But definitely thank you for giving it a try. You might remember how we did it in Coulomb's law on chapter 21, like the first day of chapter 21. That might help you. Anyone? How about if I did RP minus RDL? You see that RP minus RDL, since RP minus RDL is defined to be RP plus the opposite of RDL. So that would make the head of RDL be down at the opposite end at the origin. And then that would mean the tail of RDL would be at the point DL, and its head would be at the origin, which is the tail of RP. And then the head of RP would be at the other end, namely P. So I think you can see that that is the right vector. Now, it happens to be like Coulomb's law, it happens to be a 1 over r squared law, where r is the distance between the differential line segment DL and the point P. Therefore, its distance is actually the magnitude of RP minus RDL. But because I'm using RP minus RDL as my direction, when I did this cross product here, that actually gives me the correct direction of the magnetic field, which is how I taught y'all that other version of how to determine the magnetic field as a result of a chunk of current, other than using the one where I just make a fist and have my thumb lay along the current. There's another one I did on the 26th, I believe it was, where I was using another version, the right-hand rule like this, to show you the direction of B. So that RP minus RDL, when I take the cross product DL cross parentheses RP minus RDL, that actually gives me the direction of the magnetic field. But again, it's the magnetic field magnitude should be just the DL divided by the magnitude of the distance squared, and then times mu 0 I over 4 pi. But I've already got an extra magnitude of RP minus RDL in the numerator. So what I'd have to do is take RP minus RDL, and I've got to cube it to account for the extra one that's above. Your book does the same thing, but it just blatantly calls RP minus RDL, just calls it an R hat, and then it puts the equivalent of RP minus RDL's magnitude in the bottom. It just puts that squared, which would be fine. But to make this vector RP minus RDL a unit vector, you have to divide it by its magnitude, which is why I've got it cubed here. So that's actually the law of Biot-Savart. So remember the vectors, specifically R sub P is from the origin and that's any coordinate system you choose to make it. So it's just a vector from the origin to P, which is where you wish to know the magnetic field. Okay, and then you got RDL, which is from the origin to the tail of the DL vector. And then you've got DL, which is a tangent vector along the wire and points in the direction of the current I. Okay, any questions on that? All right, so that's our magic law of Biot-Savart, and notice it's really kind of scary looking. It's the cross product with a differential vector. Then there's two other vectors, and then you got to take a difference of those two vectors, and then you got to take the magnitude of those two vectors and cube it. So it's a lot of stuff going on, but it looks a lot scarier than it is. In reality, it's just a matter of prescriptively going through the formula and finding the little parts and then doing it. Now there's a very limited number of these problems that we can solve without using computer techniques. So that's part of the reason why I'm so stingy about not putting my answers to my test banks and my practice test banks and stuff like that out there, because there's literally just a very few that we can do. And the more the universe gets saturated with the solutions to these, the less chance people have to learn how to do this stuff on their own. So I'm going to go ahead and apply it now to what one of the few cases that we find is quite simple. And I'll explain it to you this way. If you remember, the cross product is a process, a mathematical process where you take two vectors and it spits out a third, technically a pseudo vector, but a third vector. And that third vector is perpendicular to both of the first two vectors. Its magnitude is equal to the area of the parallelogram formed by those two vectors. But more specifically, it's a way that we in physics use to pick off components of a vector that are perpendicular to each other, because we already had a way of picking out the components of two vectors that were parallel to each other. That was the dot product, and also called the scalar product. But now we also have the cross product, and the cross product allows us to find any two vectors A and B, and it allows us to multiply either A times the component of B parallel to A, or B times the component of A parallel to, or excuse me, I said parallel, sorry about that. Let me rephrase that. So the cross product allows us to find the cross product of two vectors, A and B, and the magnitude of that cross product is equal to the magnitude of A times the component of B that is perpendicular to A, or it allows us to find the product of the component, or excuse me, the magnitude of B times the magnitude of the component of A perpendicular to B. So that's what I mean when I say things like it's for picking off perpendicular components. A lot of P's in that in that little three words scenario there, but that's what we're going for here, and that's physically why we use it. We use the cross product for picking off perpendicular components, and we use the dot product for picking off parallel components. Okay. So one of the examples that we found that makes the Biot-Savart law quite easy is basically if you have a DL vector that is either parallel to the RP minus RDL, are parallel to it, are anti-parallel to it, meaning parallel but in the opposite direction, then the DL cross the parallel or anti-parallel vector will always be 0, so you get no contribution. So if you combine a circuit of wires in such a way that all the wires have current running either parallel to the DL vector, or parallel to the RP minus RDL vector, anti-parallel to the RP minus RDL vector, then those parts will be 0. And if you can manage it and have the rest of the parts be perpendicular to RP minus RDL, then the cross product is really a moot point. And makes it quite easy. So let's go ahead and show you an example of that. This is an example. So what we're trying to do is we're imagining a wire that's lying in the plane of the page. The wire starts at the top left corner. It's a current going straight downward, and then it makes an arc of radius r to the right and down, and it makes a quarter arc, in other words, a quarter of a circle, and then it hangs a left, and the current goes to the right, and then it hangs a left again, and now it makes an arc of radius 2r. It's not to scale, by the way. You'll notice the radius of the inner arc is actually 3 squares, and the radius of the outer arc is only 5. It should be 6 if it's really 2r, but that's okay. We're not supposed to necessarily draw the things to scale anyways. And it carries a current I, and specifically, according to this question, we would like to know what is the strength of the magnetic field right there at the center of both of those circles, but in the plane of the page. So basically, we're looking for the magnetic field at that dot right there. Okay. Well, I've drawn all this out a little bit with coordinates and stuff of that sort, so I'm going to steal those real quick. Actually, I was playing around with it earlier and playing with my drawing skills and stuff of that sort. So we can start off by putting it in a coordinate system, and that's what I've done here. Is I've drawn a coordinate system, and I've even labeled my individual vectors as I defined them on the previous page. So I can say, copy this. Whoa, I did not mean to do that. Okay. So I'm going to go back to that page, and I'm going to paste that picture in if I got enough room. If not, I'll just put it on the next page, and that'll be fine. So paste. And I've actually blown it up quite big, specifically so we can see details. Okay. So yeah, it fits fine. What I want you to see here is I'm starting off with a little bit of arc that's on the inner part, and I'm showing my vectors. So remember, the vector RP points from the origin to the point where we wish to know the magnetic field. Can anybody tell me what the x component of the vector RP would be? RP points from origin to P. Man, I wrote which without H in there. That's bad. So anybody want to tell me either the X or the Y component, for that matter, of the vector RP? Anyone? Anybody want to type it on the chat? Okay, so the vector from the origin to P is a vector from the origin to the origin. Therefore, its length should be 0. And in fact, it's called the 0 vector. So what we're going to do is we're going to say R sub P is equal to the 0 vector. Now, anybody want to try to guess and tell me what R sub DL looks like? So again, this is the vector R sub DL. It points from the origin to the tail of the segment DL. I've drawn the segment DL in purple, and since it's basically defined by a arc length, which we're sort of assuming is so small that the chord and the arc length are the same thing. So the magnitude of DL is RD theta. But now you see the purple vector. Can you possibly, looking at these, looking at this drawing of RDL, can you tell me what the x component of RDL is? Notice my theta is not in the normal position. Okay, well, let me help out a little bit. So what we're imagining here is there exists a vector, RDL, that points from the origin to the tail of DL as drawn here in green. My contention is that RDL is this vector right here. Well, that's the y component of it, I should say. So I drew that in a dark blue because it happens to be in the positive direction. And I'll also draw this one in a dark blue because it happens to be in a positive direction as well. So can anybody agree with me when I say that the x component of RDL is R, big R, times cosine, or excuse me, big R times the sine of theta? Anybody agree with that? RDL sine, thank you. Yes, and now if you take the RDL, again, whose length is R because of where it's at, if you take that RDL and now you try to find the y component, notice it's pointing in the positive direction, so we just say plus, and this time it's going to be R cosine theta. And then that'd be J hat. So we now have RP, we now have RDL, and we don't have DL yet. We've got to work that out, which I sort of did already for you guys. But DL is that little itty bitty purple vector. And that little itty bitty purple vector, notice it's tangent at the tail end. And of course, it's an arc, so the other end won't be exactly on the arc anymore. But what we know is the length is going to be RD theta. So if I only use sines and cosines, that would make, depending on how I do it, of course, that would likely make a unit vector. So I could just multiply the magnitude of the vector times the unit vector, and that would give me the actual vector. So we already determined that the magnitude of that vector is RD theta. So I'm contending that if you look at this, notice I've drawn another X and Y coordinate system, the same as what we had. I just moved it up there to the tail of the DL vector. And I've also extended RDL to show that that angle turning clockwise from the positive x-axis is what we're calling theta. And then, of course, the y-axis and the x-axis are perpendicular. So the next angle from the dashed line down to the x-axis would be 90 minus theta. But notice that angle is adjacent to the angle that we need. But that angle is basically between the extension of RDL, which is the green dashed line, and the purple line, which are perpendicular. So if the one between the dashed line and the x-axis is 90 minus theta, then the one between the blue x component of DL and DL is 90 minus parentheses 90 minus theta, which is just theta again. So that's how I got that little theta. You can see that the cosine is actually touching the blue side, which is the x-axis, and it points in the positive direction. And you can see that the sine is opposite the red side, but the red side is pointing down. So we get DL vector is actually the magnitude of DL times cosine theta minus sine theta j hat. So I can now write that DL vector is equal to R d theta times cosine theta I hat minus sine theta j hat. Anybody have any questions with that? Now you can tell we're going to have to do this again for the little bit between R and 2R along the x-axis, and then for the arc from the x-axis back up to the y-axis, and then a little bit from 2R to R. We're going to have to do it again, but we should learn enough from this one where it'll make it a lot easier. So anybody have any questions on this? All right. Well, how about this? Let's say RP minus RDL. Let's calculate that. We're going to say RP minus RDL, because that's a vector in the Biot-Savart formula. Notice we have RP minus RDL. We also have DL. I've now figured out DL. I've got RP and I've got RDL. So I've gotten all the three vectors. Now all I got to do is compute the difference and then compute the magnitude. So the difference, I'm going to take RP and subtract from it RDL. And that's just 0 minus R sine theta I hat minus R cosine theta j hat. Now, the last thing we got to calculate is the magnitude of that vector. So can anybody either use your magic mathematics of geometry to figure out the length of RP minus RDL, or can look at the figure and figure out what the length of RP minus RDL is? That's actually the easiest way. Remember, RP is the zero vector. So it's just a dot at the origin, basically. And then the RDL points out a distance from P to the DL. So you might be able to figure out what the length of that vector is from the diagram. Anybody have an answer for that? Taylor, maybe?
R?
Yes, that's it. It's just plain R. Yeah, good job. So now we've got all the parts we need, and we can even start to make sense. Notice the Biot-Savart law says that our direction is going to be DL cross RP minus RDL. RP minus RDL we see is just that negative R sine theta I hat minus R cosine theta j hat, which is basically negative RDL. So it's the green vector, but with the head at the opposite end. So if you take DL, which is that little purple vector, and you use the right-hand rule with that one being the index finger and the opposite of RDL being the middle finger, then your thumb points in the proper direction. So when I do that, my DL vector goes this way, my RDL vector goes this way, excuse me, and notice my thumb points into the page, which according to this would be the negative k hat direction. And that's exactly what we expect for this particular piece of wire, because if you grab that particular piece of wire with your right hand and your thumb pointing down, because that's the direction of the current, you would see that it goes in and down through the page in the middle of the arc and then comes out on the outside of the arc. So yes, that's exactly consistent with all that. And we're ready to roll. So now I can calculate B as follows. So let me change colors here real quick. So solution, which we've already started, obviously, but B is equal to the integral of dB, which equals mu 0 I over 4 pi times the integral of dl cross RP minus RDL over RP minus RDL magnitude cubed. So we can go ahead and just to tear this apart a little bit, it'd probably be smart to go ahead and compute DL cross RP minus RDL. And this will give you yet another way of calculating a cross product that hopefully you're somewhat familiar with, but you might not have seen it before. Okay, so it's a nice little way of doing it. So I'm going to copy my DL vector, which if you remember was R d theta times cosine theta minus sine theta. So R times d theta, that's the magnitude, times cosine theta I hat minus sine theta j hat. And then I'll close off my square bracket and I'll put a cross product. I want to double check, make sure that's right. R d theta cosine theta minus sine theta. Yep, that's right. And now my RP minus RDL is, this is going to have a mutual factor of R. And then notice the R is the magnitude. It's actually going to have a mutual factor of negative R. I'll put that out in front as well. So negative R. And then instead of that, now I just have sine theta I hat plus cosine theta j hat. So sine theta I hat plus cosine theta j hat. Okay. So the fact that the cross product, like the dot product, happens to be an actual linear operator tells us that we can pull all the non-vector stuff out in front of the vectors and do the math accordingly. So what I'm going to do is I'm going to use our FOIL method, if you will, and notice that right from the beginning, we've got a common factor of negative R and R d theta. So all of that can come out in front, and there's going to be more too, but those are common to everything. So I'm going to write negative R squared d theta out in front of everything. And now I'm going to write, let's do it like this. It'll be cosine theta I hat minus sine theta j hat crossed with sine theta I hat plus cosine theta j hat, like that. And I'll just put this here. Okay. So now I just use my FOIL method as I was talking about a second ago. I've got to do this one to hit that one. Then it's got to hit that one. And then this one's got to hit this one. And then it's got to hit this one. So we'll proceed as follows. Hopefully it works out into something nice. I still have the negative R squared d theta. Has anybody seen any mistakes anywhere so far? I did make a mistake on this one. I was working it yesterday in class for my other students, and I still haven't tracked down what happened on that one. In fact, I was trying to work it before class started, but I got sick today and ended up not being able to prep as much as I could other than the drawing. So anyways, what we're going to do first is notice we have a cosine theta times a sine theta. That's again using the linearity of the cross product. So I'm going to say sine theta, cosine theta, I hat cross I hat, which, remember the right hand rule. I did tell you that this guy, the index finger, is the first vector in a cross product, and the thumb is the answer. The second finger is the second vector, but it doesn't actually have to be perpendicular, even though we normally draw it perpendicular. It doesn't have to be. The one thing it shouldn't be is parallel, because if it's parallel, then you have the two vectors that are taking a cross product are parallel to each other. And as I told you, cross products are meant to pick out the perpendicular components of vectors. So if they're parallel, there is none. So the answer would be 0. And that's exactly what happens here, is you get I hat cross I hat, which basically gives you 1 for the magnitude of I times 1 for the magnitude of the second I times the sine of the angle between them, which is 0, and therefore you get 0. Oops, I wrote theta there instead. So sine of 0 degrees, and that gives me 0. So we're done with that part. Now the next term will be cosine squared theta. So I'm going to say plus cosine squared theta. And then that's going to be I hat cross j hat. Now, this one is the very definition of a right-hand rule. So I hat cross J hat, if you stick your index finger in the direction of X hat, which would be to my right, and then you stick your middle finger in the direction of Y hat, which would be up, then the thumb actually points out, which is our K hat direction. So this answer is just 1 times 1 times the sine of 90 degrees in the K hat direction. This one would have been no direction whatsoever, the first one we did, but this one actually gives us a K hat. So the answer just turns out to be K hat. So that's the second, the first one multiplied by the second one. Now I've got another one. I'm going to say plus, and I'm doing the second term in the first vector times the first term in the second vector. So I get a negative sine squared theta. So this will be negative sine squared theta times j hat cross I hat. And I think I found the mistake I made yesterday. J hat cross I hat, just like we did before. Notice it's in the opposite order though, so you end up getting negative K hat. That's one of the rules of cross products. A cross B is equal to the negative of B cross A. So we've got that. And then the last term is negative sine theta times cosine theta times j hat cross j hat, which I'm going to not even waste my time writing and just say it's the zero vector. Okay. Any questions on that? So what we end up getting, even though it was kind of complicated to do so, what we end up getting is quite nice. We get negative r squared d theta. That's the thing that's multiplying by everything. And then I just get the second and third terms, which notice the negative k multiplied by the negative sine squared theta makes it a positive sine squared. So I'm going to get just plain k hat times cosine squared theta plus sine squared theta, like that. And everybody knows what sine squared plus cosine squared is, right? Anyone? Everybody wants a victory, right? Sine squared plus cosine squared equals
1.
There you go. Thank you, somebody. Appreciate it. Yeah, I'm sure you all knew that, but I'm trying to get you somewhat involved so we can sort of make some sense out of it. So all that nastiness, that horrible nastiness turned out to be something really simple, negative r squared d theta. That's important. That's an important thing to learn here. So let's go back and now put this back into the answer. So b is equal to the negative, or excuse me, is equal to the integral of db. And as we said, that's equal to mu 0 I over 4 pi. Now I'm going to take times the integral of dl cross parentheses rp minus rdl. That's what I just calculated was rp dl cross rp minus rdl. And I got negative r squared d theta k hat. And now I've got to divide that by the magnitude of RP minus RDL, which luckily one of our students said was R, which is a constant. So that's really nice. And it's going to be cubed. So I get R cubed like that. So now what I have is negative mu 0 I over 4 pi R. Notice the two R's on top canceled out, leaving one R on the bottom. And then the k hat is out in front. So we already got our direction established, and we get the integral of d theta. And I'm going to integrate it from theta equals 0 to just pi over 2. Notice the way I define theta, it starts off at 0 and then it goes up to 90 degrees. And of course, 180 is pi, so 90 degrees is pi over 2. So you can see that this integral will be super easy. It's going to be negative mu 0 I over 4 pi r. Now the integral is just going to be pi over 2, and then all that times k hat.
you can see that this pi is going to cancel out with this pi, and this 2 is going to multiply by r. And ultimately what we get is b due to inner part is equal to just mu 0 I over 8 r k hat. So notice what all happened there with that arc is basically we ended up just getting d theta times mu 0 I over 4 pi r, and then something to specify the direction. So let me write that out. We got mu 0 I over 4 pi r times the angle times the direction vector. So the direction vector that we worked out turned out in this case to just be negative k hat. The theta that we worked out was pi over 2. So that's a ramification of what we just did. When we're doing an arc, the dl vector is always going to be perpendicular to the rp minus rdl vector, as long as, again, you're doing it to the center of the arc. So you should be able to always compute that, just making sure you use the right r and the right theta. Now, let's look for a second at the piece along the x-axis, and I'm going to call this piece, that one was 1. This piece is 2. This piece will be 3, and this piece will be 4. So this was part 1. For part 2, notice dl vector, which is a vector that points along the wire in the direction of current. It has to point in the I hat direction because the current is going in the positive x direction. And its length would be just plain dx because we're lying right along the dx. Why wouldn't we use that? So it's going to be just dx I hat. And now rp is again the 0 vector. And then rdl is going to be basically r plus x, right? Because it's got to go at least r to get to that little segment, and then it's going to go an additional x. But notice the r has to point to the tail of the dl vector, so it's going to be r plus x, and then it has to be along the x-axis, so we know that's going to be in the I hat direction. Now, the reason I did all that is I wanted you to see that now when I do dl cross rp minus rdl, I get essentially dx I hat crossed with negative r plus x I hat. So it's an I hat vector crossed with an I hat vector, which is equal to 0. In other words, I'll just say it's 0, but I'll remind everybody that A cross B magnitude is just equal to A times B times the sine of the angle between them. So in this case, this would mean some magnitude times some other magnitude, doesn't really matter, times the sine of 0 degrees, which equals 0. Okay, so that's why we got that. So part 2 makes no contribution. I'm going to do part 3, or excuse me, part 4, just because that's super easy to figure out. So part 4, dl points in the direction of current. Notice in part 4, that means it goes in the negative y direction. So dl is going to be negative dy j hat. RP again is going to be equal to the 0 vector. And then we have RDL, which points to the little DL vector, which, by the way, is lying right along the x-axis, or excuse me, right along the y-axis. So it'll be at a value of y that's r plus some y. So I'm going to say it's equal to r plus some specific value of y. And then that's the sort of length of it, if you will. And then that's going to be in the negative j hat direction. So I'm going to put it like this. So that's roughly RDL. And what that means is DL cross RP minus RDL is equal to negative dy j hat crossed with negative of negative is going to be positive. I'll put a square bracket around this, positive r plus y j hat, which gives us again the 0 vector because it's j hat cross j hat. And this one's 0. Does that make sense to everyone? So we've now worked out, if you look back here, we've worked out the part 1, which is that little arc. We've worked out part 2 and part 4. Now all we got to do is work out part 3. I think you can see that part 3 is going to be very much like part 1, except notice the direction of RP, or excuse me, the direction RP is still going to be 0. RDL is now going to be twice as long, but the same vector. DL vector is still going to be the same thing, except its length is not RD theta, but rather 2RD theta. And we'll go from there. So we could go through that process, do that cross product and all that again, but that would be not using what we learned right here. So let me write this again. This is what we learned, that when we're doing arcs, okay, when we're doing arcs and we're finding the magnetic field at the center of the arc in the same plane as the arc, then this is the answer. So all I've got to do for part 4, oops, I probably want to use another color. Actually, I think I will use blue. So this is technically part 3. I just called it part 4. Sorry about that. But this is technically part 3. What we know is the direction of this one, since the current is going in a counterclockwise direction around that arc, whereas before it went in a clockwise direction, we now see it should be in the positive k hat direction. So the direction is positive k hat. And then all we've got to do is say the magnitude B is equal to mu 0 I over 4 pi times the radius of the arc, which in this case is 2r, and then times the angle, which in this case is again pi over 2. Okay, so what you can see here is the pi will cancel out with the pi again. And now instead of having 4 times 2 is 8, we've got 4 times 2 times 2, which is 16. So that implies this part will be B outer is equal to positive mu 0 I over 16r k hat. So when we add those two, we're going to get mu 0 I over 16r minus mu 0 I over 8r, which could be called 2/16 r. So we do 1/16 R minus 2/16 R gives us negative 1/16 R. And the final answer will be B total equals B1 plus B2 plus B3 plus B4, which you know is B1, which was negative mu 0 I over 8R K hat plus 0 plus mu 0 I over 16R K hat plus 0. So B total is equal to negative mu 0 I over 16R K hat. Any questions on that? All right, so let's I don't see anybody asking any questions, I don't see anybody typing any questions, but I just want to read. Whoa, I'm gonna put that way over there. Must have flipped to too many pages. Let's see if I can do this and copy it back to the right place. What the heck? I'm just going to do this. I'm going to move page to trash. Zoink. Now it's good. Okay. So just recap the actual Biot-Savart law, which is mu 0 I over 4 pi times dl, which is a differential tangent vector along the wire carrying the current, or just the current in general. It doesn't necessarily have to be a wire. So that's what dl is, and it has to point the direction current's going. The RP points from the origin to the point where you wish to know the magnetic field. Oh, that's a wish. That's why I said that. It's not which. I just forgot part of that. Where you wish to know the magnetic field. And then RDL is a vector from the origin to the tail of DL. And then you just one by one compute all those things, calculate it all out. And a lot of times you can see all this stuff in advance and you don't have to actually carry out all these nasty cross products and all that good stuff. If you do, then yay, that's good. You've learned how to do that, but ultimately you'd like to get fast enough where you don't have to do all that. And that's sort of the tricks that your author Giancoli is doing in their examples. So definitely work towards that, read their examples, see if what I did helps you understand that better, and see if what he does helps you understand this better. And ideally, the holy grail would be you guys being able to shut your book and be given such a problem and do it all on your own. But I got a couple other problems I want to work before then. I've only got about 22 minutes left. So first off, I'm going to consider another scenario. I'm going to have another current carrying wire, for instance, and this current carrying wire is going to carry a current vertically. So what we're going to say is the current is right here like that, and it actually goes on for infinity. Okay. And what I'll do is I'm going to say the current is I, and it's pointing upward. And I'm going to say it also goes to infinity the other way. Again, that's not the current, that's just the wire itself. And now I'm going to draw a coordinate system. Okay, my coordinate system is basically going to be right here. I will call that, let's call this one the y-axis. And then coming out of the page will be the x-axis. This is the y-axis. And then you can probably see that along this wire is the z-axis. what I want to do, again, remembering the wire goes from negative infinity all the way up to positive infinity, what I would really like to do is say this is my point P right here. And it's a distance. Notice the symbol I use here. The distance is going to be R. Okay. And the reason I'm using R, actually, let's use a lowercase r. The reason I'm using R is I know what this result was. Remember, we learned it in the previous chapter on magnetism. The answer is supposed to be mu 0 I over 2 pi R, and we're supposed to use our right-hand rule where I stick my thumb up along the current since the current goes up, and I curl my fingers around, and my fingers curl around in the direction that the magnetic field goes. So that means, for instance, at that point P, I expect the magnetic field to point into the page. Out here on the x-axis, which is right in front of the wire, it should point in the positive y direction. Back in the negative x-axis, where I'm behind the wire, it would point in the negative y direction. And if I was over on the negative y-axis, it would point out of the page. Everybody agree with those directions? Anybody have any problems with that idea that that's the directions? Okay, if you're not getting that, you definitely got to work on your right-hand rule some more. But that is what it is. And in this case, since we've drawn our axes this way, you can't use Cartesian coordinates, for instance, to spit out cylindrical coordinates or spherical coordinates. So as far as this figure is going to know is the magnetic field as a result of this at point P should point into the page, which is the negative x hat direction or the negative I hat direction. So that's what we're going to expect. And it should be equal to mu 0 I over 2 pi R. So let's work that out. So our solution is, again, this is another example. Okay. What is B at P? That's the question. Solution. We know that B is equal to the integral of dB, which equals mu 0 I over 4 pi times the integral of dl cross rp minus rdl, all that divided by the magnitude of rp minus rdl, and that will be cubed. So our job, first off, is to calculate the vectors dl, rp, and rdl. So can anybody, for instance, tell me what the vector rp would be? That's probably the easiest one. RP, remember, is a vector that starts at the origin and points to the position P at which you wish to know the magnetic field. I've got P drawn. We're going on the assumption that the I and the lowercase r are quantities that we know. So, you know, when I do things theoretically like this, then there might be some ambiguity and whether we know things or not. So this variable I, we know, and this variable R, we know. Okay, so can anybody tell me what the vector RP would be? And R is just a number, by the way. I know I've got a couple of students in there that can answer this. All right. right. Can anybody tell me how far P is from the wire? Specific thing about this, vector is obviously if you know the magnitude, then you can just multiply it by a unit vector pointing in the right direction. So how far is P from the origin, which is where the wire is?
R.
R. So the length of RP should be R. And it points from the origin to the point P. So do you know of a unit vector that points in that direction?
J hat.
Exactly. So RJ hat is what we're getting at. Now RDL, this part's a little more confusing. That's why I didn't try to make you guys do it. But what you can imagine, for instance, hopefully my program will let me draw this close to it and correct it. That looks good. And I'm going to say the wire is just getting a lot thicker than it was. Maybe that's one way of thinking about it. So what I'm going to do is I'm going to imagine a little segment of the wire right here. Okay. Now the current's going up. So I'm taking that little segment of wire and I'm saying that's how long DL is. So I'll use the purple like I used before. I'm going to say DL is that vector right there. Can anybody guess what I'm going to use for the length of that vector?
DZ.
DZ, exactly. So I'm going to write DL as DZ. And I want it to point parallel to the current, which we decided was going up. So which direction is it going to point?
Positive.
In the positive Z direction. And do we know of any unit vectors that point that way?
K hat.
Exactly. So that's all this is just literally bit by bit putting the things apart. Now, there's a reason, one, that I put the current along the Z axis. And when you have that as a case, then there's an automatic simple variable that you can use for the distance between the origin and the DL. Anybody want to guess what the length of RDL is? What's the most natural distance to measure from the origin up along that particular axis? Taylor, you know that one?
These are the most natural distance.
Uh-huh. What's the most natural variable to use to indicate the distance vertically along that axis?
H.
H would be fine. The only thing is we actually have a variable already. We don't need to bring in another one. There's a distance that they measure from the origin.
Oh, Z.
There you go. That's the one. So I'm going to put right here that RDL has a length Z, and its unit vector is what?
Okay.
So that's it. That's our vectors. We just figured DL was in fact DZK hat. We figured out RP, all that good stuff. I can even show them on here. I think I was using green before, so I'll try to use green again. So this vector right here is RDL. This vector right here from the origin to P is RP. And then the distance that we're talking about is actually along this line right there. Anybody want to guess? You can actually use your formulas like you want because we're really trying to find RP minus RDL here. But I think you can do it even easier if you recognize what RP minus RDL is. Anybody want to take a guess at what that magnitude is?
Be the square root of RP squared plus RDL squared.
Yes. And what is the length of RP?
R
And what is the length of RDL?
Z.
There you go. So would you say Z squared plus R squared?
Yes, sir.
That's it. That's all you got to do, guys. It's pulling teeth, but this is pulling teeth because it's the first time you've done it. Some maybe more than just one person is getting it, I hope. But that doesn't mean there's anything wrong with the people that didn't get it. It just means that, hey, I haven't seen this. This looks kind of foreign to me. I've got to equate myself with it. So that's all you got to do, guys, is you got to think, how long is the vector? What direction does it point? Because the easiest vector you can ever make is one that you know its length and you know a unit vector that points the same direction it does or the opposite direction. Because if it points the same direction, it's just the length times that vector. If it points the opposite direction, it's just negative of the length times that vector. So we've got all the bits and pieces. Let's go ahead and compute what DL cross RP minus RDL is. Oh, I didn't calculate RP minus RDL. So let's do that real quick. RP minus RDL. So RP we see is RJ hat. So that's going to be RJ hat minus RDL, which is Z K hat. So now we can say DL cross RP minus RDL. That's another vector that we can compute. So we know that DL is DZ K hat. We're going to cross product that with, and I'm going to put this in square brackets. It's going to be RJ hat minus Z K hat. Okay. Now we're going to use our sort of distributive property, if you will, like the FOIL method, and we're just going to have to hit those two. So this is going to give us R DZ and then K hat cross J hat. And then the other one's going to give us a minus ZDZ. And this one's going to be K hat cross K hat. And I suspect you all know what K hat cross K hat is. I want everybody to know that's ZDZ there. I could have actually written it a little bigger. Let's see if I can make it a little bigger and still keep things decent looking. So that's what that is. So we now have computed basically the bits and pieces of the cross product. So we see K hat cross K hat is just going to be the zero vector. So that part's not going to matter. Now we've got K hat cross J hat. If you actually stick your index finger in the direction of the Z axis, which is K hat, that's up. And then you put your middle finger in the direction of the J axis or the Y axis, which is to the right, you'll see that your thumb points into the board, which is the negative Z hat direction, which is what the negative X hat direction, or negative I hat, which is what I told you that we predicted. So this part's just going to be negative I hat. So now I've got basically this whole cross product is just negative R DZ I hat. Tiffany's back. Okay, so now that I have this, we can say B, which is equal to the, actually, I don't have to do that part. I already said that part. It's equal to mu 0 I over 4 pi times the integral of DL cross RP minus RDL. We just computed that. That's negative R DZ I hat. Notice we did get a negative I hat direction, which is exactly what we expected. And now we have to take the cube of RP minus RDL, which would be Z squared plus R squared to the 3/2 power. Okay. So that's what we got to do here. The good news is that looks like a scary integral, but the good news is it's not, because it actually happens to be more or less the same integral we did on the first integral of chapter 21, which is when we were using Coulomb's law to calculate, oddly enough, the electric field due to a current carrying wire that was infinitely long. So again, we see the symmetries between the electric field and the magnetic field. In this case, notice the R isn't really the problem. And in fact, the fact that I have a capital R and a little r various places is problematic. That means your instructor is a goober. So let me fix that. All of them are supposed to be little r, because remember, we made the distance little r. And I'll do it here as well. So that's going to be a little r. We only got about 5 minutes left, and I actually had a second problem I want to solve. Might not be able to get to it, but that's okay. I can point you to one on my channel. So what I'm going to do is I'm going to pull the negative, the mu 0, I, and the r out in front, and the I hat as well. And then under that, I'm going to have 4 pi. And now I'm going to take the integral. And technically, I'm going to integrate from z equals negative infinity, which I really shouldn't write that, but we're just going to say negative infinity to positive infinity of dz over the square root of, I'm going to change the order here for a reason. Namely, the reason is that I don't like writing it the other way. And that's the 3/2. And now we're going to use a trig substitution. Let z equal r tangent theta. Then dz is equal to r secant squared theta d theta. So that's the trig substitution we're going to make. And in fact, this has ramifications. For instance, if we look back at our coordinate system, we can see that it would be this axis, there's x, or excuse me, that's y. I forgot I drew it the way that I did. And this is z. Tangent theta would be z over r, and r is the distance that we said was along the y-axis. So this distance right here is r, and this distance right here is z, and this angle right here is theta. And therefore this side, in case we needed to know the sine or the cosine or something like that, this side is the square root of r squared plus z squared. So that might come in handy. And of course, I made it so small that it possibly can't. But anyways, I think you're getting what I'm trying to say here. So I can just do, well, I don't know why. All of a sudden, it doesn't want to erase, even though it erases every time I touch it. R squared plus z squared is what's going on there. So I can now use my new variable that I'm doing with this integral. And that's going to give me, I'll put it down here. That's going to give me negative mu 0 I r over 4 pi. And I'm going to leave the space under there because I think you can see that when I made this substitution, this becomes r squared times 1 plus tangent squared theta, like that, raised to the 3/2 power. So the r squared raised to the 3/2 power in the bottom makes r to what power? Anyone?
Three?
Yes. So it should make the r cubed in the bottom. And this is worrying me because I'm supposed to have a single r in the bottom. Make sure I didn't drop any r's anywhere. RDL was in fact ZK hat, that's right. RP was in fact RJ hat, that's right. That all looks good. Okay, we'll just have to wish that I hope that everything pans out. So let's work this out. So we got mu 0 I r over r cubed, and then times I hat. And now I've got the integral of dz. That's where it came from. Remember, dz is r tangent theta. Oops. Tangent theta d theta. So there's the extra r we needed. And then that all will be divided by 1 plus tangent squared. But I think you all know that 1 plus tangent squared is secant squared theta. Therefore, it's to the 3/2 power. That means it's going to be a secant cubed theta in the bottom. Oops, it's not r tangent theta. It's r secant squared theta. Stupid head. Sorry about that. I remembered something wrong. This is going to be r secant squared theta d theta, because that's what dz was. And down at the bottom, I'm going to get a secant cubed theta. And of course, that means, notice now I can get rid of this guy and this guy with that one, and that's just going to leave r to the 1 in the bottom. So now I have negative mu 0 I over 4 pi r I hat times the integral of 1 over secant theta, because this turns out to be a secant theta in the bottom, but 1 over secant theta is cosine theta. So this is 1 over secant theta, which is cosine theta, d theta. And instead of integrating from z equals negative infinity, we're going to integrate from theta equals negative pi over 2 to theta equals pi over 2. Now we can do that, or we can just realize that cosine theta is an even function, so we could actually integrate from 0 to pi over 2 and multiply the answer by 2. I'll do that just for the fun of it. So multiplying this by 2, it becomes negative mu 0 I over 2 pi r instead of 4 pi r now. And then I hat, and now I'm integrating from 0 to pi over 2 of cosine theta d theta. And of course, the derivative of sine is cosine, so the integral of cosine is sine. So I'm just going to get negative mu 0 I over 2 pi r I hat times the sine of pi over 2 minus the sine of 0. And in this case, we clearly see that that is just 1. Because that's 0. So our final answer is exactly what we said it would be. B at P is equal to negative mu 0 I over 2 pi r I hat, which in general, if we were using fancier coordinate systems, we would see that would be in the negative theta hat direction. Actually, this one would be in the positive theta hat direction. Yeah, that works fine. It'd be the positive theta hat direction, because theta is in the direction, or theta hat's in the direction of increasing theta, which goes counterclockwise as seen from the positive x-axis towards the y-axis, in other words. So we would see that that actually points exactly the right direction. So we could also say B at P is equal to mu 0 I over 2 pi r theta hat, for those of you who are in the know with regards to cylindrical coordinates. Any questions on that? All right, well, the last part I was going to do was one for a loop of wire, which is pretty much what we did already. Our time's run out. You guys are free to go. I'm just going to put on here exactly what video you guys should look at to get that last example. So let me stop sharing, and then I'm going to go to my YouTube channel and pull up exactly the one that you guys should watch. That way you'll at least have it on this recording. And I'm going to do a search for Biot-Savart.
and Biot-Savart and Ampere's law. So there's actually, I'll just tell you that. Just do a search for Biot hyphen Savart, Savart, and you'll see I'm looking at 1, 2, 3, 4, 5 examples of me using the law of Biot-Savart. Of course, each one of them will have probably 3 examples in it, maybe 4. You're looking for the one where it's just a loop of wire laying like in the XY plane. Okay, so give that one a try. That way you'll have a little bit more experience. You guys are free to go. We'll finish up this chapter in our next meeting on Tuesday. Have a great weekend. Keep an eye on your email in case I tell y'all any good news. And thanks for coming, everybody. I'm
Hey,
waiting here
Professor
until the last person leaves. Yes.
I got a quick question. I don't know if you can share. How did you determine it was negative I hat? I still struggle with
The right hand rule.
the whole right hand.
Okay, no problem. That's actually, yeah, that's I'm glad you asked, because that's really the whole point of this is I know students are having problems with the right hand rule. So I was hoping more people would ask. So thank you for that. I'm going to share now. Let me take a sip of that drink since my throat's so dry. Okay, so it should come up any minute now. There it is. Okay, so it's this problem right here. If you take that wire, which we can treat as if it's this pencil, okay, notice the wire is pointed up like this. My thumb wants to point in the direction of the current. So I'm going to stick it right there. And then I see this because I'm grabbing it with my right hand. Notice that says it goes around this way. So this spot right here is literally what we would see on the y-axis where I have drawn. And you're supposed to imagine concentric circles going around the wire. So tangent to a concentric circle right here would be directly into the page. So if you pull it out here, it's still going to be directly into the page, but that is in this coordinate system in the opposite direction as X. You see that, Tony?
Yes. Okay.
Does that make sense?
So when you cross K hat and J hat, you just doing that. You just put in, the thumb where the current is going, and if it is going to be on the left and the right, if it's on the right, it's going to be inwards to the page. If it's on the left hand side, it will be coming out of the page.
Right. So one thing you could do, you see your DL vector. It's the RP minus RDL is that green diagonal line that goes from the little blue blocks to the P. The head, I didn't draw it on there, but the head would be right there by the P. So you can also lay your finger along that diagonal vector, your index finger, and then you turn your middle finger in the direction of DL. And in order to do that, you'd have to turn your hand up this way. And you see now that for the DL to go in the upward direction, I'd actually have to, wait a second. I can't do it with my shoulder right here right now. But the main thing is you're supposed to do DL so we can point it up that way. And then we can do RP minus RDL, which means I've got to turn this way. And my finger now points, it's bigger than 90 degrees because that middle finger is going along the diagonal, but the index finger is going up and my thumb is pointing in. So this is the P diagonal vector right there. This is the DL vector, that index finger. And then my thumb points into the board. And that too is the negative I hat direction. Does that make sense, Tony?
Yes.
Okay, hopefully one of those two will sit well with you or something like that. There's also neat little tricks you can do when you're doing the cross products of those little unit vectors. If it's a cyclic permutation, then basically everything works out nicely. So for instance, I cross J is IJ, and then the next one, of course, they all have to be different. The next one's got to be K.
but that's like 1, 2, 3. So that's the way they're supposed to be. So you just call it positive K hat. But if it's JI, then the missing one's still K, but because it's 2, 1, that's not a cyclic permutation of 1, 2, 3. So you have to use a negative K hat for that one. So that's another way you can do this on a piece by piece method when you're actually doing that term by term and doing a cross product. Maybe that'll help you. If not, I can explain it more if that way helps you a little bit. But yeah, most of the time you can sort of figure it out just from knowing your right hand rule and then using the little rule AB sine theta. So any other questions?
No, that'd be awesome. Thank you. It helped me. It explained a lot.
Thank you. I'm glad to help you. See you,
Yeah,
Tony.
really good.
You too. Hi, Tiffany. How you doing?
Can you hear me?
I can now. Yes, ma'am.
Okay, wonderful. I actually was just getting on here to ask you if you had a chance to read the email I sent you the other day.
Yes, I did see it. I haven't composed a way of saying it, but I would tell you that don't worry about it. You're going to be fine. There's nothing. I mean, you're going to be fine. Okay. You're generally top 3, top 4 in the class. So things work out pretty nicely that way. Let me stop recording this because we're talking about stuff that the world doesn't have any necessarily any rights to know. So I'm going to stop recording this real quick. But yeah,